Welcome to my projectbazaar.com. Let us discuss about the weighted sum rate maximization for MIMO downlink systems powered by renewables. Let us discuss about the abstract of the product. Energy efficiency and spectral efficiency plays an important role in wireless communication systems. The increase in demand for frequency bands with high data rate requirements, we are in need to efficiently utilize the available spectrum with better energy efficiency. So, cognitive radio networks plays vital role in utilizing the available unused spectrum efficiency with better energy efficiency. Existing work investigated power allocation schemes are a single cognitive radio user based MIMO OFDM system. In this project, the system MIMO downlink systems powered by renewable energy resource is proposed. An efficient algorithm is developed to obtain the optimal strategy on the uplink and downlink duality and a Lagrange relaxation based subgradient method. And also, optimal resource management for smart grid power MIMO system is greater importance of future green wireless communication. A novel framework is put forth to account of stochastic renewable resources, dynamic energy prices, as well as a random wireless channel. Based on practical models, the resource allocation task is formulated as an optimization problem that aims at maximization the weighted sum rate of MIMO broadcast channels. A two-way truncation mechanism and storage units are introduced to accommodate the RES variability. In addition to system operating constraints, a budget threshold is imposed on the worst-case energy truncation caused due to the possible adventure nature. Capitalization on the uplink and downlink duality and a Lagrange relaxation-based subgradient method, an efficient algorithm is developed to obtain the optimal strategy. Generalization to steps of obtaining variable channels and on-off transmission are also discussed. Numerical results are provided to cooperate the merits of novel approaches. Let us discuss about the flow diagram of the product. So first of all, this is a system model. In the system model, it's split into three models. One is a MIMO broadcasting model, and another one is a RES harvesting model, and another one is a energy store and energy cost model. In MIMO broadcasting model, consider a MIMO downlink system where a base station serves a total of K mobile users. The base station is equipped for NT transmission antennas, while each of K users has a NR receiving antennas. So, different from where the base station is purely powered by harvesting the RES, here we assume the base station is jointly supplied by the persistent power sources from the main grid as well as the harvested renewable energy. So specifically connected to the main grid via two-way energy trading, the base station is further supported by one or more local energy harvesting facilities. So moreover, the base station is equipped with local storage unit, so that is does not have to consume or sell the harvested energy on the spot, but can save it for the later. And also, the base station is aware for the downlink channel state information using effective channel estimation, for example via limited road feedback. So, the energy truncation information including the buying and selling prices can be collected by the base station with installed smart meters. The base station control is chain charge accurate. The base station controller is in charge of coordinating the energy trading and communication for optimal resource management. We are assuming that the slot of length wireless transmission is large enough to accommodate the Shannon capacity achieving the encoding scheme. Consider a finite scheduling horizon, so with a normalized of stall duration unless otherwise specified. Hence the terms energy and power will intelligently insert CAD. So and then RES harvesting model. In RES harvesting model, let ET denote the energy harvest during the slot T-1 which is available at the beginning of the slot T. Different from the common harvested energy, but time slot is accurately known per year. We assume that E is known as an inherently and uncertain nature of RES. However, it is assumed that it is very possible to. And then energy store and energy cost model. In energy cost model, in addition to harvested RES, the main grid can also support the base station energy demand. Given the required energy PGD, harvested energy ED, and the battery charging BBD, the short energy that can purchase from the grid or surplus energy that can be sold back to the grid. Not both the storage and energy non-negative, and we can have that most one of the positive at any time. And then ensure all the parameters for related to the MIMO broadcasting model, RES harvesting model, and energy storage and energy cost model. So and then derive the optimization problem for power allocation. So this optimization problem of power allocation is derived the equation. So that is, we will optimize the location of resources for the small grid powered MIMO base stations, specifically through fixing the optimal covariance matrix, transmitter power, and battery charging energy. Base station wishes to maximize the total throughput of the downlink transmission, subject to given the budget of host gas of transmission costs. So the correct the achieved transmission rate for all the users. By introducing the auxiliary variables, the resource allocation task of interest can be formulated as a optimization problem. So in this topic, the optimization problem will be discussed in the process. So if the interference threshold is less than, is again to go to the loop and following the process. If the interference is less than the threshold, so maximum weighted sum rate will be calculated and then finally allocated to the performance analysis. In this performance analysis, basically calculated the sum rate versus to the transmission antenna or receiving the antenna. So this is the flow diagram of the product. Yeah, here we discuss about the running procedure for the product. So click the main file and run. So now by executing the file, many outputs are displayed. So these are all the outputs related to our flow diagram. So I think there are 7 figures related to a diagram. That is, so yeah, this is the first figure. That is a sum rates for MIMO base station subject to the GC. That is a K is equal to 10 and NT is equal to 2. NT is a transmitter antenna, that is equal to 2, and K is a number of nodes. So this one is a propose, and this is a no energy trading, and there is a no storage. So in our propose, there is a renewable energy. The renewable energy compared to all the existing results, that is very high compared to the no energy trading and no storage. So x-axis is depending upon the GC and the y-axis is depending upon the sum rate, that is megabits per seconds. So this is the first graphs describe about the procedure. Yeah, this is the second figure. Sum rates for MIMO BC subject to GC. K is equal to 10 and T is equal to similar to the figure 1. This is the GC and this is sum rate megabits per seconds. So no RES, that means renewable energy sources not depending on the structure. So this is a plotting of pink color. So that is a no RES depending upon the antenna, and also a MIMO concept of the wide rate sum rate of the calculation. So this is the third figure. That is the sum rate of MIMO BC subject ET, that is energy transferring. K is equal to 10 and NT is equal to T. So here blue color is denoted by the propose, and red is denoted by no energy trading, and black is no storage. So these are our existing, and this one is our propose. So comparing to all this, is a sum rate by calculator. Basically these all the concept calculating only the sum rate. So sum rate is depending upon the megabits per seconds. So this is a S for up to 1 to 10. This is 65 to 90. So up to this, this is our propose method. Propose method is high comparing to all the existing work. So this is a figure displaying about the sum rate. Yeah, this figure denotes the sum rate for MIMO BC subject to ET, which is the same, but the K is equal to 10 and NT is equal to 10. So in the previous figure, that is NT depending upon the NT is equal to 2. That is a transmitting antenna, that is 2. Here NT is equal to 10. So that is a sum rate is a blue is our propose, and red is a no energy trading, and no black is a no storage. Compared to all the existing results, propose one is as a best result. So this is describe about the K equal to 10 and NT is equal to also 10. Yeah, this figure describes about the K equal to 10, not NT equal to 10. This is a K equal to 10. So this is also calculating about the sum rate. Blue one is a propose. Similarly, the same process. For example, this is one is a pink color. So the pink color is denoted as the no RES. Already we combined in the figure 2. So that is a no RES depends. There is a no energy renewable energy resources. So here excess is denoted by the NT. So for example, NT is the transmitting antenna side. So it is a NT. So this figure is about the K is equal to 10 for the proposed work. Yeah, this figure is denoted by optimal power schedules of power transmission and CT. So K equal to 10 and NT equal to 2. This is a P scheduling, that is a kilowatts per hour. This is a time slots. So comparing to all the time slots, the power schedule, what's happened here. So this what's the time slot in for example, this is a 4. So in the 4 time slot, it's a briefly decrease. In 3, there is an increase. So these are the comparison between the time slots and the power scheduling of the process. So here the previous schedule is comparing to the power slot, but in this schedule, so battery state depending on the time slots. So here the time slots 1 up to 1 to 8. In this time slot 1, so battery state is 15. So time slot 2, the battery state is 25. So comparing to similarly to all these time slots, optimal power schedule calculation for k equal to 10 and NT equal to 2. So this graph is procedure for the battery state only. So battery state is comparing for the kilowatts per hour, and these are the time slots in per hour. So this is a calculation of optimal power schedules of PP. So these are the running procedure for the product. Thank you for listening this video.